Have you ever just stopped and wondered, what are you made of? What's your desk made of? Or the air you're breathing right now? Well, today we're going to find out. We're going on a journey to find the ultimate building blocks of, well, everything.
It sounds like such a simple question, right? But the answer is kind of mind-blowing. What are you made of? What about the sun, the stars, the entire universe? The answer to all of that starts in the exact same unbelievably tiny place.
And yep, you guessed it, that place is the atom. This is our ground zero. If you want to understand how anything is built, I'm talking a distant galaxy or the phone in your hand, you have to start right here. Okay, so what even is an atom? The best way to think about it is like the ultimate Lego brick. It is the smallest possible piece of an element you can have. You can't chop up a gold atom anymore and still call it gold. It's the absolute fundamental unit. So let's take a look inside one. Here's a classic carbon atom. Right at its heart, you've got this super dense core called the nucleus. And then you see those things zipping around the outside? Those are the electrons. But the real action, the stuff that defines the atom, is packed inside that nucleus.
All right, let's break down what's in there. We've got three main players. Protons have a positive charge. Neutrons have no charge at all. They're neutral. Makes sense, right? Both of them are crammed together in the nucleus, and they each have a relative mass we just call 1 to keep it simple. Then you have the electrons with their negative charge orbiting the nucleus. But here's the crazy part. Their mass is so tiny, we're talking almost 2,000 times smaller, that we just ignore it. It's like weighing a bus and then worrying about the weight of a fly that landed on it. It just doesn't really change the total. And this all leads to a really important rule in the world of atoms. They love being balanced. In a normal, stable atom, the number of positive protons is perfectly canceled out by the number of negative electrons. The charges are equal, so the whole atom has a neutral, zero charge. It's perfectly happy. So we've met our three subatomic players, right? Protons, neutrons, and electrons. But one of them is the undisputed MVP. It's the one particle that single-handedly defines what an element actually is. And that's the proton. The number of protons is like an element's fingerprint or its social security number. It's unchangeable. An atom with 6 protons is always carbon. Period. If you could magically add another proton, it's not carbon anymore. Bam! It's nitrogen. The proton count is everything. So, when you look at the periodic table, how do you read this stuff? Well, think of it like a secret code for each element. X is just the symbol, C for carbon. Z is the big one. That's the atomic number. And that's just the number of protons. That's its identity. And A, the mass number, tells you how heavy the nucleus is. It's just the protons plus the neutrons added together. Simple as that.
Okay, so we've established the proton number is locked in. It can't change. But what happens if we start messing around with the other two particles? Well, that's where things get interesting, and that's where we get concepts like isotopes and ions.
So first up, let's talk isotopes. These are basically family members of the same element. They have the same number of protons, so a carbon atom is still a carbon atom, but they have a different number of neutrons. That means it's a little bit heavier. It changes the mass number, but not who it is. A great example of this is carbon-14, which has a couple of extra neutrons. It's super rare, but it's what scientists use to figure out how old ancient artifacts are.
So here's the bottom line, the key difference you need to remember. Isotopes, you're changing the neutrons. This affects the atom's mass, but not its charge. Ions, you're changing the electrons. This totally messes with that perfect electrical balance we talked about and gives the atom an overall positive or negative charge.
Now, this brings up a really cool question. If isotopes have different masses, different weights, why in the world do they act exactly the same in a chemical reaction?
The answer is one of the most important rules in all of chemistry. Ready? Chemical reactions are all about the electrons. That's it. It's not about the nucleus, it's about those outer electrons. And since all isotopes of an element have the same number of protons, they also have the same number of electrons. So they behave identically. The neutrons are just along for the ride. All right, we've gone deep into the atom. We've seen what it's made of. Now it's time to zoom back out and see how these tiny, tiny building blocks come together to create the entire world we see around us. So matter pretty much comes in 3 main flavors. First, you have an element. That's a pure substance made of just one type of atom, like a bar of pure gold is just gold atoms. Then you have a compound. This is where things get interesting. 2 or more elements chemically bond together in a fixed ratio, creating something totally new. Think about H2O. 2 hydrogen atoms and 1 oxygen atom bond to make water, which is nothing like hydrogen or oxygen gas. And finally, you've got a mixture. This is just a jumble of stuff, not chemically bonded. Like sand and water at the beach. You can still see the sand, you can still see the water, and you could separate them pretty easily.
And this image here really tells the whole story, doesn't it? We start with individual atoms. They can bond together to form molecules. When you get a huge collection of the exact same molecule, you have a pure compound. And when you just throw a bunch of different things into a container without them bonding, you just get a mixture. It's a really simple, beautiful hierarchy, and it all starts with that one humble atom.
So, there you have it. We've just learned the fundamental rules for how matter is built. But it makes you think, right? If these are the rules, what amazing things can we create by bending them or even breaking them? And that, my friends, is the magic of chemistry. Thanks for joining me on this deep dive.